A data structure is said to be linear if its elements form a sequence or a linear list. For example, array, linked list, stacks, queues, etc. all come under the category of linear data structures. The operations on linear data structures involve traversal, searching, insertion, deletion, sorting, and merging. By traversal, we mean that we can visit every part of the data structure. By search, we mean that we can traverse the data structure and search for a specific element. By insertion, we mean we can add new elements to the data structure. By deletion, we mean we can remove any element from the data structure. Sorting means rearranging the elements is also allowed, and merging means combining two similar data structures into one. In today's tutorial, we will be discussing about how this linear data structure array is stored in the computer's memory. I am Anandita and welcome back to my channel Computer Engineering Made Easy. Please stay tuned till the end so that we can learn the row and column major ordering of arrays. By definition, an array is a kind of a data structure that can store fixed-sized sequential collection of elements of same type in contiguous memory locations. It is used to store a collection of data but is often more useful to think of an array as a collection of variables of the same data type. A specific element in an array is accessed by an index. All arrays consist of contiguous memory locations. The lowest address corresponding to the first element and the highest address correspond to the last element of the array. Arrays can be 1D, 2D, 3D, and even 4D. In case of one-dimensional arrays, the indexing grows in only one direction. For two-dimensional arrays, there are two parameters maintaining the array indices. The first one is the row index and the second one is the column index. In case of three-dimensional arrays, which is basically multiple two-dimensional arrays layered one after the other, we have got three dimensions. The first index maintains the row index, the second one indicates the column index, and the third one indicates the depth index. Also, in many real-time applications, we use time as the fourth dimension. In such cases, we can have the values of the three-dimensional array get changed with every instance of time. In such cases, those data structures are called four-dimensional arrays. Whatever be the dimension of the array, arrays are always stored in memory locations following linear order. So even if it is a two-dimensional array or a three-dimensional array, the entry corresponding to each cell is stored linearly in the computer's memory. Indexing in array can be categorized into three broad categories. The first category is the zero-based indexing. This type of indexing happens when the first element of the array is indexed by the subscript 0. Many languages like C, C++, and Java use this type of indexing. The second category is the one-based indexing. Here, the first element of the array is indexed by the subscript of 1. Some developers believe that starting array indexing at 1 is natural for counting. Hence, it is used in languages like MATLAB, etc. The third category is n-based indexing. The base index of an array can be freely chosen in this case. Usually, programming languages allowing n-based indexing also allow negative index values, and other scalar data types like enumerations or characters may be used as array index. Let us consider two examples. In the first one, we declare an array ARR of type integer and size 10, and then we try to access the array index -2. In this case, we will get an invalid or out of range error. This is because the scope of the program only have the array positions 0 to 9 at its disposal. On the other hand, if we declare the array ARR of size 10 of type integer and then we set a pointer p to refer to the location ARR2, the user is actually allowed to access ARR0 since it is within the scope of the program. Hence, if we try displaying the value of p-2, it will actually refer to the location ARR0. Hence, in this case, even though we are using negative index, it is still valid. In computing, the methods for arranging multidimensional arrays in linear storage, such as random access memory, are either row major or column major, as shown in the figure. In row major order, the consecutive elements of the rows of the array are contiguous in memory. This approach is usually followed in languages like C, C++, Python, and Java. In case of column major ordering, consecutive elements of the columns are contiguous in the memory. This approach is usually followed in languages like Fortran and MATLAB. In matrix notation of array, the first index indicates the row and the second index indicates the column. Example, A1, 2 is in the first row and in the second column of the array A. Even though the row is indicated by the first index and the column by the second index, no grouping order between the dimensions is implied yet. This convention is carried over to two-dimensional arrays in computers languages, although often with indexes starting at 0 instead of 1. An obvious way to order objects with more than one attribute is to first group and order them by one attribute, and then within each group order them by another attribute. Not all attributes have to participate in ordering. If more than one attribute participate in ordering, the first would be called the major and the last the minor. If two attributes participate in ordering, it is sufficient to name only the major attribute. When applied to two-dimensional arrays, in case of two-dimensional array, if the entries are made row-wise, we therefore call it row major, and if the entries are made column-wise, we call it column major ordering. In case of row major ordering, all elements of the first row come before all elements of the second row, and so on. And within each row, the elements are ordered by column. As one steps through the consecutive memory locations, the index associated with the major order varies slowest, and the index associated with the minor order varies fastest, unless there is only one index value in that dimension. For example, in the array A, having the first row elements as A11, A12, A13 and A21, A22 and A23 in the second row will be stored as shown in the figure for row major and column major ordering. If we consider the addresses to range from 0 to 5, in case of row major order, the values stored in the addresses will be A11, A12, A13, A21, A22 and A23 in the corresponding addresses. However, in case of column major ordering, A11 will go to address 0, A21 will go to address 1, again A12 will go to address 2 and A22 will be going to address 3, A13 will go to address 4 and A23 will go to address 5. In case of a single dimensional array, considering that the addressing scheme follows decimal system and the array is an integer array for which each cell takes 4 bytes of space, the address of the fifth cell of the array will be 120 as shown in the figure. In order to calculate this address, what we actually had to do is find the difference between the lowest index and the ith index of the cells and then multiply them with the size of each cell. Here, multiplication of the difference value with the size of each cell is actually going to give the number of bytes that we need to traverse from the base address in order to reach the ith cell. Hence, the address of the ith cell will be obtained by adding the base address to this. In this case, the value of I is 5 and the lowest index of the array is 0. Hence, the difference between 5 and 0 is 5. And since the array is an integer array, we multiply it by 4, that is the size of each cell is 4, and therefore we get the value 20. That means we need to traverse 20 bytes from the 0th cell of the array to reach the 5th cell. Now the base address of the 0th cell of the array is considered to be 100. So we add this 20 to 100 to get the address 120. Similar concept is also used in case of two-dimensional arrays. In case of two-dimensional arrays, in order to find the address of a cell, we need to know the row as well as the column index of that particular cell. Say the row index is I and the column index is j. This means in order to reach that particular cell, we have to traverse all columns till the i-1th row in case of row major ordering. And apart from that, we also need to traverse j-0 columns in the ith row to reach the desired cell. So in order to do so, we first identify i-0 into n, where i-0 provides us with the number of rows which needs to be traversed completely, that is for all n columns, in order to reach the desired cell. And j-0 indicates the number of cells that we need to traverse in the ith row in order to reach the desired cell. Therefore, i-0 into n plus j-0 provides us with the total number of cells that we need to traverse from the 00th cell of the array to reach the desired cell. Once we get to know the total number of cells that we need to traverse, we multiply them with the size of each cell. And that is going to give us the number of bytes that we need to traverse from the base address in order to reach the desired cell. Thus, the address of the desired cell will be obtained by adding the base address to this. And thereby we get the formula for calculation of the address of a particular cell if it is stored in row major order. Also, in this case, the assumption is that the array index starts from the 00th cell. But that may not be the case always. For that, we have got a modified version of this formula which we will be discussing shortly. Coming to the column major ordering, in order to find the address of the cell in the ith row and jth column, we have to traverse all m rows for j-1 columns. And after that, we have to traverse some more rows which is given by i-0 in the jth column. So we have to traverse some more cells given by i-0 in the jth column. So the total number of cells that we need to traverse in order to reach the desired cell is given by j-0 into m, and added to that will be i-0. So once we get the total number of cells that need to be traversed from the 00th cell, we multiply it with the size of each cell, and therefore we get the number of bytes that we need to traverse from the base address of the array. Therefore, the final address of the desired cell can be obtained by adding this number of bytes to the base address, and thereby we get the formula for column major ordering in case the starting cell or the starting indices of the array is 0 and 0. Now, if the array index doesn't start from 0, we consider a separate formula for this. Basically, we consider the lowest row index to be LR and the lowest column index to be LC. Accordingly, the formula for row major system can be modified as address of Aij is equals to base address B plus storage size, that is the size of each cell given by W, into n into I minus LR plus J minus LC. Similarly, for column major system, we can write the modified formula as address of Aij will be equal to the base address B plus W into I minus LR plus M into J minus LC. Now, addressing does not always start from 0. We can have any kind of addressing. So, if the LR and LC are not 0, in such cases, we have to identify the values of M and N separately before proceeding with the address calculation. In such cases, we find the number of rows M given by UR minus LR plus 1, and the number of columns N is given by UC minus LC plus 1. Now let us take an example where we have an array X whose indices range from minus 15 to 10 row-wise and 15 to 40 column-wise. Here each cell requires 1 byte of storage, and if the beginning location is given by 1500, we will try to find the address of the location X1520. In order to do so, since the array index doesn't start from 0 in this case, we have to first find the total number of rows and the total number of columns. The total number of rows, say M, will be given by the formula UR minus LR plus 1, and on substituting the values of UR as 10 and LR as minus 15, we get the value of M as 26. Similarly, for the number of columns, we get UC as 40 and LC as 15. So on substituting the values in the expression, we get the value of n as 26. Now, to find the address of X1520 using row major ordering, we have the base address B as 1500, W as 1, I as 15, J as 20, LR as -15, LC as 15 and N as 26. So we substitute these values in the expression for finding address of Aij using the row major ordering, and we get the resulting value as 2285. Now, in case of column major ordering, we have the values of B as 1500, W as 1 byte, I and J as 15 and 20 respectively, LR and LC as -15 and 15 respectively, and the value of M as 26. On substituting these values in the expression for calculating the address of Aij using column major ordering, we get the address value as 1660. So this 1660 is basically the address of the location X1520 of the array X. With that, we come to the end of our today's tutorial. Hope you have enjoyed it. Please make sure that you hit the like button, share it with your friends and subscribe to my channel.